In these next few videos, I'm going to provide a broad level overview of the things we've learned in the last few weeks for exam 3. And as with previous reviews, don't expect every possible thing to be in these next few videos. That's of course what the lecture notes and the videos from previous weeks themselves are for. But I do want to do a broad overview of the concepts and things we've talked about. And I'm actually going to start with week 10 instead of week 9. So we learned these things talking about the behavior of muscles, like force length, force velocity, and all that first, then the structure of muscles. And in this review, I'm going to start with the structure and then go back to the behavior of muscles, if you're all right with that. So we learned that muscle fibers muscle fibers like this, are made up of these individual tubes that are stacked next to each other like a fistful of pencils. And these are called myofibrils, these individual tubes. That's the myofibril. And if you look at each of those tubes close up, you see that they are made up of these repeating units like this. And we call those sarcomeres. And down below here, I have an illustration of what the anatomy of a sarcomere is. Now, the important things to know about this are, number 1, the myosin right here, that protein. Number 2, the actin right here, that protein. Number 3, titin, this protein right here. And hopefully, as you recall, the myosin protein has these heads right here that grab onto actin and then pull like this with the power stroke, and the same thing happens the other way right here. And that is how individual sarcomeres contract. And as you can probably recall, when those sarcomeres get stacked up end to end, the whole myofibril will contract. And then because you can add up the force of individual myofibrils, like this one and this one and this one and this one and so on, then that creates a large amount of force in this muscle fiber. So you don't need to worry too much about, which is the Z disc and the H zone and all of that, and the M line and the I band. Don't worry about that too much. Do worry about what the actin is, what the myosin is, what the titin is. Remember, titin is this kind of rubber band-like material that keeps the myosin proteins centered in the sarcomere. And we can attribute much of the passive stiffness of muscle to the titin proteins. So we also talked about the some of the things that are missing from, or maybe not labeled here. Maybe we can label them. This stuff, this kind of netting that's going around these myofibrils, that was the Sarcoplasmic Reticulum. And we conceptualize that as like a bag of calcium, just sitting maybe, let's say sitting like out here, a big bag of calcium ions, waiting for an electrical signal from the central nervous system via a motor neuron, and that triggers the release of calcium ions out into the muscle. And what happens there, if you recall, there are these, at the microscopic level, there's these proteins, tropomyosin and troponin. Again, the specifics of those not super important. What is important to know is that calcium is like this throttle for controlling the activation level of your muscles. Because you could imagine, right, if there's more calcium being released, say, over here on this muscle fiber versus over here, or if this whole muscle fiber gets stimulated to a greater degree than its next door neighbor muscle fiber, you'll be able to control in a smooth, continuous way the level of force production in an entire muscle. So the dynamics here, this is this idea of excitation and activation. So we thought of this electrical signal going to the sarcoplasmic reticulum as an excitation from the central nervous system. If you've done motor control, you can think of that as an action potential. And the translation of, okay, the calcium comes out and the troponin and tropomyosin do their thing, and then the myosin heads start producing force on the actin filaments. That is activation. So the actual amount of force produced is activation. The electrical signal is excitation. And we'll talk in a future video about specifics of that. Okay, and then so this is like microscopic structure of muscle. And then we also talked about the macroscopic structure. So we've zoomed out quite a bit here. There's like tendon on either end of a muscle. And we saw that there's this thing called pinnation, where the individual muscle fibers, like here, they are not necessarily always perfectly aligned with the direction of the whole musculotendon unit. Sometimes they are, like in this case. They are aligned. But in cases where they're not aligned, what we call this misalignment. Or in other words, we call this angle right here, we call that the pinnation angle, and we can say this is a pinnate muscle. In this case, a unipinnate muscle. Remember, there's also bipinnate and multipinnate muscle. And one of the advantages that pinnated muscles have is that they are able to produce more force even with the same anatomical cross-sectional area. So if you took a slice of this muscle, that cross-sectional area is about the same as a slice of this muscle. However, because muscle fibers produce force in the direction of the fiber, what's relevant for force production is this cross-sectional area. Or you could think of it as the number of muscle fibers that are stacked up in parallel to each other. So notice how there's many more stacked up in parallel in this muscle than in this muscle. And that's a function directly of what the pinnation angle is. Usually we measure that pinnation angle relative to going just straight to end. We'd call this, on the left, we'd call this like 0 degrees of pinnation. And this is, I don't know, maybe 20 degrees or whatever it is, whatever you'd measure. So that's pinnation. That's probably the most important broad, like structural muscle property. We incorporated that into this model over here of muscle contraction that explained this interesting phenomenon that muscles do not actually change their volume when they contract. So the idea was we had one tendon going off like this, the other end of the musculotendon unit going off like this, and then the muscle fibers are arranged at an angle like this, and that angle is the pinnation angle. It's labeled phi here. So that's that pinnation angle. And then when the muscle contracts, you could think about it as like this part just sliding this way. And when the muscle lengthens, you could think about it as it stretching out like this. So broadly, this was the structural properties of muscle as we have learned them in the last few weeks. And then in the next video, we'll review the behavioral properties, so force length, force velocity, and so on.